Okay, so welcome colleagues. My name is Johnny Ho. I'm the facilitator for today's seminar. And today we are very glad to have Professor Angus YIP to have a presentation for us to introduce his recent work on all the organic photovoltaics. As you can see, the title is pretty fundamental all the way to niche applications. So let's welcome Professor YIP.
Okay. First, I would like to thank Johnny for the very kind introduction. I am Angus YIP from South China University of Technology. So it's my great pleasure to be here today to introduce to you our recent work on the organic photovoltaics. So I would like to use the first two slides, trying to introduce our university to you first. I think many of you may be familiar with that. It's very close to Hong Kong in this, in Guangzhou, it's the Pearl Delta region. We also now is the Great, right, Great area. And this is the Guangzhou city, and our university actually is very close to the city. Yeah. And this also a very beautiful campus. And I started to work on SCUTs in 2013. And I joined this state key laboratory of luminescence materials and devices. In China, we have this state key laboratory very focused on a certain area. In our laboratory, we are working on organic electronics. So including this OLED display technology and also organic solar cell. So my focus is more on the organic solar cell, but I also, when I joined the university, I also work on the other two areas. This is my group. I have three different areas working in my group. Today I will have a more main theme talking about organic solar cell, but I also work on the perovskite solar cell, which is one of the very nice magic material discovered or rediscovered, right, in the past couple years. And I also have about the other 1/3 of my group working on perovskite light emitting diodes. And I think if later on any faculties are interested in these two areas, I can also individually talk to you. And for the organic solar cells, I kind of briefly summarize several important directions, right, for this OPV study. And the one highlighted with the blue color are more fundamental research area. And also the one with the red one is more about translational research. So therefore, I am interested in both, right, from the fundamental to also applied research. And besides this material development, I'm not a chemist, so I work with a lot of material chemists working on their nice material, and then I cover the other few area, including morphological study and also device engineering, device physics and optical management, and also stability study. The fundamental part, as I mentioned, I am working in the state key laboratory to perform this fundamental research. I also kind of run a center to promote the translational research, which is about this module design and roll-to-roll printing, and eventually trying to find a niche market for this OPV application. So therefore, I also run this innovation center for printed photovoltaic, right? The goal is trying to use this roll-to-roll printing to produce the organic solar cell in large scale. So today I will focus on these four areas. In the first three of them are the very important parameter for the solar cell application. We need to have a very high efficiency device. We need to find their unique application, and also we need to have durability, right? Their stability. So I will talk about three structure properties relationship regarding to these three areas. The first one is trying to understand from the molecular crystal structure and the charge generation properties relationship in the champion organic solar cells. And then in the second one is talking about more related to the optical modeling I will show you how we can use this high throughput optical modeling, trying to help us to design the perfect, right, or the best device architecture to achieve the desired optoelectronic properties for different applications, tandem cell or semi-transparent solar cell. And the third one is I will talk about how we can engineer the different interfaces between the material and within the device so that we can enhance the stability of them. And then I will also have a very brief update on the module development in our group. So the motivation, I think everyone can agree that renewable energy is very important for us, and the solar energy is very abundant, which is considered to be one of the most important renewable energy. And the PV industry in China or in the world actually was doing very good in the past 10 years. Nowadays, right, they can already bring down the solar energy cost that is compatible, right, with the fossil fuel energy. Maybe I take out my mask. It's not easy. Okay, so you can see right now, right, their cost actually is even lower than the projected cost, right? Therefore, you can expect that the solar industry will continue to grow, right? But they will also encounter some bottleneck because when you have the scale is increasing, eventually the large scale energy storage will be the bottleneck for the application of the solar energy, because now we are installing this solar farm in remote area, right? Therefore, there are lots of discussion start to talk about bringing the solar energy into the city. That is about the distributed or the microgrid PV technology. Then we can generate the energy and then just use it right away within the city. So this is very related to the topic I would like to talk about today. Is a building integrated PV. We need to find some new technology that can be integrated with different building and also architects. So so here I would like to give you one example. Typical crystalline silicon panel, they are not that good looking. So it's difficult to put it on the wall, right, of a building. So there are lots of companies start to think about whether we can develop new PV design, right, to apply for whatever the building need. I think Tesla also announced that they will invest a lot on this solar roof, right, and also combined with their solar battery. And then this is the thin film technology. Another several of a big company in China also promoting this BIPV, and this is based on a CIGS or this CATL, the second generation thin film technology. So you can see at least the looking is better. So if you put it on the wall, it still look like a building. So about 2 years ago, right, Hong Kong also launched this incentive, right, solar subsidized, right? If you install, right, the solar panel in your house, you generate electricity, you can sell it back to the grid, right? Therefore, I also kind of contact a local company. I am now working as a scientific advisor for the company, trying to bring in new PV concept, right, from wherever the connection I have in China for the PV manufacturer. And this is one good demonstration. Now you can see that the CIGS flexible panel, you can laminate it, right, them into this curvy glass to make a module that can be used for the solar tile. Okay, so this is one good demonstration. But if you look at the house here, right, we actually get a lot of complaint by the neighborhood, right? They said that the house look different to our one, right? It's not that beautiful. Therefore, we suggest to the PV manufacturer trying to really tune the color, right? These are small tricks, right? We can tune the color of this panel. So now, right, they are producing some red or orange solar panel, right? This tile, this is kind of the first ever, right, color solar tiles, right, installed in the world, right, which is in Honolulu, right, in kind of a typo. So you can see it will be a very big market, right? All the house actually, they need this beautiful, right, color. So this is one very good example, right? The BIPV application, you should have some technology very different from the traditional.
Can I stop with a question here?
Yeah.
Since you have a gray color, so which means the gray color is reflected out. And the band gap of the silicon is like 1.1 and 0.7 EV.
Yeah.
That's in the great region.
Yeah.
So there is no photon for your photovoltaic.
Yeah. So actually we do optical tricks, right? It looked like red, but actually on the glass only very small dot of the red color are on the panel. So the efficiency actually is not that big different for the black one. Yeah, so this is how I think later on I will also introduce more about optical engineering, why optical management is important for tuning the different appearance of the solar panel. Yeah, so this is working very well for this one. So for today's topic, we are talking about organic solar cells. So the difference between organic and inorganic material is organic material can be made very flexible. So we are looking for the unique properties of OPV and trying to identify the right market for that. And we are not competing with silicon solar cell, right? We are not looking for this solar farm application, but more on this, based on this highly flexible, non-toxic, and also aesthetic properties of OPV. They have two major markets. The first one is this wearable portable power source, or you can even use it as an indoor light harvesting or power generation device, which is very important for the Internet of Things application. So that is one possible application. And the other one actually is tailored for BIPV, because for organic thin film, we can make it as a semi-transparent. Okay, so therefore, you may potentially open up a new direction for making PV gas. Okay, so the glass can also generate solar energy. So these are the two major directions. And of course, right, for the solar farm application, perovskite PV module may be the one suitable for that, because they have a very high efficiency already. And then if their cost and also their efficiency can be compatible with the silicon solar cell, they may have a chance to compete with the silicon solar cell in this large-scale deployment application. So this is the state of the art of OPV development, and particularly for the past 2 years, there are lots of new material developed, and then help us to significantly improve the OPV efficiency. So you can see that now the efficiency for single junction or tandem cell already reach up to 17 to 18%. And for module, they can also improve the performance to over 12%. And there are lots of commercial development over the past around 20 years, mainly in Europe and also US. But at that time, right, they do not have high efficient material, but they already proved that, right, this technology can be applied for this roll-to-roll printing, right? And their module with a very good encapsulation, they can also have a very good lifetime for over 10 years. This is the Konaka, the first company trying to commercialize the OPV, and their module is still working very well, okay? And our group also showed that for new material, high performance material, if we do the right material engineering and device engineering, we can also have a lifetime over 20 years. And actually, for all those important milestones, we also have certain participation to achieve all those milestones. So go back to the fundamental, right? Organic semiconductor is very different from inorganic semiconductor. And they can either be evaporate or solution process. And the first OPV device was introduced by Professor Chin Ken, right, when he was in Kodak. He used this electron-rich P-type material and also this kind of N-type material to make this P-N junction. So this semiconductor can absorb light, and then at their interface, they can generate the photocurrent. Okay, so the other one is introduced by Professor Heger and also Dr. Yu Gong, right, about 25 years ago. At that time, they are trying to mix this fullerene and conjugated polymer, right, into solution, and then they create so-called the bulk heterojunction. And later on, I will tell you, right, why we want to make this bulk heterojunction. But of course, right, the efficiency of solar cell is determined by their short circuit current, right, which is depending on how much photon you can absorb, right, the band gap of the material. But it also depends on the VOC, right. If you have a small band gap material, the voltage you can generate will be small. So we are trying to maximize JSC, VOC, and also the diode characteristic to optimize this power conversion efficiency. So one of the reasons why we want to make this bulk heterojunction, because the exciton generated in organic material is a Franco exciton. They are very localized. So if you cannot find, right, an interface between this donor and also acceptor material, which have enough energy to separate the exciton, they will just recombine and lost. Therefore, you need to create this nanophase separation with the length scale in the 10 nanometer range, right? And they need to have a continuous path so that the hole and electron can be carried out to the two different electrodes. So this is the important process for the photocurrent generation in bulk heterojunction solar cell. And of course, right, the low dielectric constant, right, large exciton binding energy sets some limitation for organic solar cell. So for the charge generation, as I mentioned, you need to have some energy offset, right, in order to separate the exciton. That's one of the loss. Another loss is the radiative recombination, which is unavoidable. Even in the inorganic material, you have around 0.3 volt of loss of that. The other one is non-radiative recombination. You try to minimize this one so that now you can reduce the total energy loss. For the case of fullerene, this C60 material, usually in organic solar cell, you need to lose. The energy loss will be in the range of 0.7, 0.8 volt. But that set a limit of the performance. However, in some of the recent replacement of this fullerene material, we call it non-fullerene acceptor, we find that we don't have any, right, energy offset required in this one. We can still have an efficient exciton dissociation. So later on, I will kind of tell you why in some of the state-of-the-art material, we don't require this type of energy offset for the exciton dissociation. So these are the OPV performance record for the NREL efficiency check. And you can see OPV actually have a 3-stage of the development, right? And the first one is still based on this fullerene material. At that time, people are trying to control the nanophase separation morphology so they can improve the performance to about 5%, right, with this PVHT. And then there is a couple years of development trying to develop better polymer donor material with better absorption, smaller energy loss, and then the performance can improve to around 10%, still based on this fullerene, right? And in about 2014, there are some new replacement acceptor molecule for replacement of fullerene. And at that time, right, people find that, right, the absorption of this new molecule can be improved, but also their energy loss actually reduced. So therefore, there are a few years, right, the performance of OPV start to improve from around 10% to about 13%. But the real breakthrough actually is coming from the last 2 years with this curve, right, molecule. Actually, this is the molecule I work with Central South University, and then we kind of, my job is trying to optimize their performance and also make a very stable device so that we can ship it to US and then get this certification from the National Renewable Energy Lab, so that we also get a point, right, mark our point, right, on this PV efficiency chart. And of course, based on this very special material, over the past 2 years, there are continuous improvement of the OPV performance, and now, right, the highest certified one is a 17.4. But of course, I know that there are more, even higher, right, efficiency device being developed. Anyway, although, right, we have a lot of effort trying to improve the performance, but the underlying principle or the fundamentals about why this new type of acceptor material has improved performance is still unknown. But if you look at this Y6 molecule, right, compared to the previous champion non-fluorine acceptor, this Y6 is smaller in bandgap. That means they can absorb more light, okay? But if you look at their VOC, they are the same, right, with this IT4S. Therefore, right, you get very good EQE, very high current density, and also maintain a reasonable VOC. So now you can immediately get the power conversion efficiency close to 16%. And we also find that, right, this type of, the red dot here is corresponding to the non-radiative VOC loss. We try to keep it small. So this Y6 material has a relatively small non-radiative VOC loss, particularly when you consider that it still have a very high external quantum efficiency with close to 90%. So therefore, over the past 1.5 years, my group really trying to, based on this properties performance relationship, we start trying to understand the molecular design and then their crystal structure, right? And then when this material blend into the bulk junction, what will be their morphology? All of this will affect the charge dynamics, right, of the for the charge separation. And then we further correlate it to the energy loss within the device. So this is a very important, actually, I would say this is the central, right, study, right, for OPV. We really need to understand based on the molecular structure all the way to the device structure. So we take this approach, start to look at the crystal structure. First is looking for this IT4F1, although it showed a decent performance in organic solar cell. However, if you look at their dimer, they doesn't really pack as ideal or what we think, right? They are more packed like a herringbone structure. So I will say that their charge transporting properties with this type of structure is not really ideal. But now when we look at the Y6, this curve, right, light structure, this is a dimer. Now it's quite interesting. They are very planar. And you can see that this dimer, they have, this is the electron acceptor unit are packing on each other to form this dimer structure. And now if we look at the extended structure, just like a U-shaped dimer structure. And now when we look at the extended structure, this one is the first plane of the crystal structure, okay? And then you have, this is the dimer, and the dimer and dimer connected to each other, okay? This is the second layer of this crystal structure. And this is the third layer. You have the molecule pointing in this direction. And then the fourth layer actually complete the whole crystal structure. And now this is a very interesting structure. I would say a very rare in the organic semiconductor to form this highly ordered network structure. And then therefore, with this crystal structure, we can start to use a DFT calculation, trying to understand how the electron and also whole transport pathway within this crystal. And the one on the left here is corresponding to the valence band or the HOMO level delocalization. And you can see that this HOMO delocalization actually is pretty good. It is three-dimensional, right? It's spread in the lateral, right, way and also in the vertical direction. So unexpected, right? They also may have a whole transporting properties, although we are using it as a acceptor for electron transport. And the one showing here is for the LUMO delocalization. So you can see the LUMO actually is more delocalized in the vertical direction, because you see that those acceptor molecule is stacking on each other. So this stacking create a very nice electron transporting channel for this material. So we kind of model this electronic coupling, where for both electron and hole coupling, they are quite similar and also quite large. That means they can facilitate a decent charge transport. And we also measure the space charge limited current for this Y6 pure film. So we observe, right, both electron and holes can transport, right, within this thin film. And the hole transporting properties is even a little bit higher than the electron transporting properties. And we further trying to look at the exciton properties. We can also calculate the exciton coupling energy, and it's also reasonably high. What does it mean? It means that the exciton can diffuse relatively fast. Okay, and if we have a very fast hopping rate in the sub-picosecond, we can reduce the exciton and the wibonic coupling with the molecule. Okay, so this is important, because if the exciton is decoupled with the vibration, we will have a more emissive exciton. Okay, so this is one of the reasons why this non-radiative loss, right, in this particular material is so good, because they are very emissive material. So we can use this time resolved PL, trying to measure the lifetime of this Y6 and also the previous IT4S linear non-fluoring acceptor. You can see the lifetime is 3 times higher than the IT4F, right? So the Y6 has a long lifetime, and the PL quantum yield is also very high, right? 5%. I think Professor Ji Yun recently published a Nature Photonic paper, exactly is talking about for the breaking the band gap law, right? It's a very small band gap material. You need to have these properties, okay? Decoupling of the ribonic and also the excitonic nature. And this material actually is also a very good infrared LED material, right? So more importantly, now we know the crystal structure. We also need to know whether this crystal structure preserved in the thin film, okay? A lot of time, if you process it in different way, they may not have the same crystal structure in the thin film. And luckily, we do this GREC study, and we find that the corresponding for the phase-on orientation. We find that we have a very good pi-pi stacking here, and also we find another characteristic peak, which is corresponding to the distance between these 2 dimers. Okay, so they can observe in the GREC, which means in the pure Y6 thin film, this material is oriented face-on, right, on with the substrate. This is good for electron transport. Okay, and we also can correlate kind of the in-plane structure. We can also correlate the different lattice distance with the in-plane structure. Further, kind of prove that, right, they have a face-on structure. And we also work with this binary. We band with the polymer, or even ternary. We also add some fullerene into the bulk junction. We can see that this crystal structure actually is quite well preserved, right, even in the brand film. So that's why I think the DFT calculation, whatever the properties we find, actually can also introduce into this brand film. So we do a collaboration with Professor John Luberda's group for doing a more detailed molecular dynamic simulation. So we just heat up the whole system to 800K, and then let it cool down slowly. It takes a couple months to do that, right? What we find out that is this Y6 molecule, right? They are packing, right? They have a 3 mole of packing, 3 dimer. Actually, all of this packing mole can correlate to the single crystal structure. So at least from wherever our collaborator told us that, they never see anything like this before for other acceptor, which means this molecule has a very strong stacking. Okay, so their packing is very close to the crystal structure. And we also simulate in the band film, right? This together with the polymer, there are polymer within it, and we also see the packing mode is maintained the same with the single crystal structure. So it correlates very well with our GRES morphological study. So this will be very useful now when we have this model. We can start to take out pieces of that to do the other calculation, which is the electron delocalization, right, within the donor and acceptor interface. Here, I show you that when we only have a monomer of the acceptor and also the monomer of the polymer, okay? So you can see that this is kind of the charge transfer exciton. The distance between this charge transfer distance is only about 2 nanometer. However, now if we have a very good packing or aggregate of this acceptor material at this donor acceptor interface, you can see the exciton distance actually is extended to about 5 nanometer. Okay, so wherever if it is extended, which means the Coulombic interaction attraction at the interface is reducing. Okay, from the monomer is 160 millieV. For this trimer of the acceptor, right, it is about 70 millieV. But of course, in the real case, I think it will have even more aggregation of that. So if this can go down to the room temperature, which means, right, even at room temperature, we already have enough energy to separate the exciton. That also explains why, right, we don't need to have any energy offset for the exciton dissociation. The material aggregation already create a loosely bound charge transfer exciton. Okay, so this is one of the reasons why this type of a new material, they are very interesting molecular structure, bringing to an interesting electronic structure, and then eventually they're favorable for exciton dissociation. And of course, we have another paper trying to further understand another mechanism, which is the self-stimulated dissociation, right, of the exciton. What we find out that is when we try to increase the excitation density for this Y6 molecule, it gets self-polarized, bulk polarization. If it is polarized, the dielectric constant increase, reduce exciton binding energy, and it's easy to separate. So there are several different possible mechanisms to show you, right, why this is amazing material, right? Okay. So here is a very short summary. With this very interesting, right, organization of the molecule, we can form very delocalized and also emissive exciton, enable very small non-radiative loss, right? And also the delocalization of the wave function, right, at the donor-acceptor interface also help us to reduce the Coulombic interaction of the charge transfer exciton. It also helps to reduce, right, the energy required to separate it, so making it as a very highly efficient material. And here is also one possible direction, right, to work on this new type of organic semiconductor. If you look at this metal organic frameworks and also this covalent organic framework, which eventually is a very big research area. Now, this very interesting non-covalent packing of this semiconducting material also create similar type of framework compared to the well study one. So this is possibly, if the chemist, right, can put more thought to design this material, you can even introduce functionality within the host, right? Now, actually, these are the side chain. If you can engineering the side chain, you can engineering the introduce functionality with that. So the advantage of this possible non-covalent organic framework is they are solution processable, right? This material, they are not processable, okay? And they are already electroactive, photoactive, right? So you can further explore, right, different functionality of that. So this is one possible future direction. Okay, so the second part I would like to talk about is optical management, which is very important for solar cell application. We need to know how the light distribute or how to maximize the light harvesting properties within the device. So we can introduce this so-called the transfer matrix model based on the light reflection and also transmission properties when it pass through an interface. Now, when we build a matrix, then we can calculate the light transmission reflection properties with this multi-layer device. So this is not new. This has been introduced 20 years ago to kind of help us to understand how this electrical field distribution, right, within the different layer. And of course, right, in order to perform this transfer matrix model, we need to get the optical parameter, including the reflective index and also the absorption coefficient with all the material we want to test, right, in the device. We can then, right, model their electromagnetic field distribution. When we further couple to the absorption coefficient with the material in the active layer, we can also find out their charge generation profile within the active layer. And we can also do a very detailed optical loss analysis or even analyze the color, right, of our device. So that is the commercial model. Over the past couple years, I have a student, right, who is very good at this mathematics. He further improved this model by trying to introduce this. The previous model is doing good, right, when the length scale of all the layers is similar. But now if you have a length scale, for example, you separate them by 1 meter, then you need to introduce another matrix, which is the incoherent layer here. So we feed in all this transfer matrix model for coherent length scale into this incoherent. Now we can expand the calculation capability. Now, for example, if you have two devices separate over 1 meter, we can still calculate the light propagation, right, for these two devices. We also trying to increase the calculation speed by a lot of modification of the code. Okay, so now we can just using a laptop, we can calculate about 50 million structure per year. So this is increased by close to 10,000 times compared to the commercial model. So this is one example. We can apply this optical modeling, helping us to design the best structure for the tandem solar cell. We know that in the tandem solar cell, right, we need to have one subcell harvest, for example, the visible light, the other subcell harvest the infrared light. And we need to have a current balancing. So that's why in the architecture, device architecture, we need to maximize the light harvesting properties of these two subcells, but at the same time, we want them to have the maximum power generation. So we can apply this model, and then you can see that we can easily find, right, the right device design that can achieve the best device performance. So we can reduce a lot of try and error, right, to do that. So we collaborate with a lot of groups working on this tandem solar cell, and I think about 2 years ago, we also published a paper in Science reporting one of the highest performance tandem solar cell at that time. So here is kind of the work. You can see we have one of the layer actually absorb only the visible light, the other layer absorb the infrared light. So when we couple them, we need to work on this all solution processing, which is not easy, but we find out the right way to class, right, 6, 7 layer, right, without destroying the bottom layer. And we also couple with this optical modeling, so we know the best architecture so that we can maximize the performance to 17%. And of course, we can do a further semi-empirical analysis. If we can further reduce the energy loss for both large bandgap and also low bandgap OBV, we can even have a performance over 22%. And I can give you an update now, it's already close to 20%, right, for this tandem solar cell. So besides the tandem solar cell, another big application is for the semi-transparent solar cell. Here I highlight some of the market analysis for this BIPV, and no matter, right, the silicon industry, they are also looking for this rooftop installation, particularly for this manufacturing plant, they have a large rooftop. However, in the city, you have this high-rise building, all of the surface are glass, okay? So they don't really have that much of a row or rooftop for installation of a traditional PV. So now you can see the area you can use for this commercial building and also the city residential building is only 10% of the total surface area of the building. That's why now if you can start to capture also using this window for PV application, you can have a loss of a new area for installing the PV. So this is one of the potential market for organic solar cell. And compared to inorganic material, a very unique properties of organic material is tunable absorption properties. Okay, so if you look at here, this is one of the absorption profile, right, with the bulk junction. We can selectively tune the absorption in the infrared, right, allowing the visible light to pass through it more easily. So these intrinsic absorption properties make it very unique compared to inorganic material, which has continuous band and always have a very strong absorption in the visible range, but low absorption in the infrared range. Okay, so now we can imagine that we can harvest the infrared light and then make a highly transparent device. So my group also introduced a new concept inspired by the material genome concept. Okay, so what we are doing here is building a database, material database, optical database. We have worked with a lot of material already. We have a lot of collaboration. So we now have over 300 state-of-the-art active layer NK value. We also have this interfacial layer, electro layer NK value. So we have a library. We also have this high throughput calculation modeling. Okay, so now what we are trying to do is instead of just making a device, we can ask the computer to base on whatever the function or the properties we want. For example, for the semi-transparent solar cell, we want to tune the color. We want it to be color neutral, or for greenhouse application, for heat isolation, we can ask the computer to find the right material and then find the right device architecture to give us the best right combination of that. And then here is one of the example, okay? And this one show you that this is a basic, right, semi-transparent solar cell device architecture. You have the bottom ITO transparent electrode, active layer here, and then you have a very thin silver film as the top transparent electrode. Okay, so the blue one itself already is a basic semi-transparent OPV. But now we can try to introduce a distributed back reflector photonic crystal. The function of that is trying to, at this interface, we reflect the infrared light back so that we improve the infrared harvesting, but we allow the visible light to pass through it. Okay, increase JSC, maintain similar transparency. Okay, so for the traditional design for this distributed back reflector, we can follow this stop band equation. Okay, you can see the transmittance and also the stop band. We can have a pretty good control of that. However, for transparency, right, our human eyes is very sensitive to the green light. Okay, so this is the sensitivity of our human eye. So now if we can design a photonic crystal that is tailored for this shape, we can actually enhance the transmittance, but also can capture some of the extra photon, right, in the red and also blue region. The stop band equation cannot make this special function. Therefore, we need to use this high throughput screening in order to achieve that. So we can ask to have this power conversion efficiency and also visible light transmittance as a function of the different thickness of the active layer, thin silver electrode, and also the photonic crystal, which means we are simultaneously tuning the thickness of this blue and also green layer. Okay, so now that will be a huge combination, right? For just tuning this 6 layer, there are 14 million of a possible device architecture. And here I highlight the power conversion efficiency and also the visible light transmittance. each of these dots corresponding to each device architecture. The good thing is you can always find the maximum, the optimal curve, right, at the top of that. That means now we don't need to make 14 million devices, right? We only need to choose it from this optimal curve, right? And then we choose several data points here, very close to this optimum curve, and then we make the device, okay? And these are the kind of whatever the different thickness provided by the computation simulation. And now, right, when we make the device, it's very close to whatever our simulation result, right? So now we can easily get a high performance device, but at the same time, we can also get a very decent visible transmittance. So here I show you that this is one of the semi-transparent OPV solar cell with 30% transmittance and also over 10% power conversion efficiency. And you can also see this is the transmittance curve, right? You can see a big peak here corresponding to the 550 nanometer, which is our eye sensitivity. And we can also see that, right? This curve is quite meaningful. This is the infrared absorbing material. This is the long infrared absorbing material. We can maintain 90% of this opaque device performance and generate about 30% visible transmittance. So that means, right, the PCE of the device doesn't really reduce much, right, when you make it into this transparent solar cell. And of course, right, we can even add more function in that. For example, if we want to introduce a high color rendering index so that wherever the device can be looking more color neutral, we can also input this value. For example, we want it to larger than 90, which is close to the neutral color. We can also ask the computer to consider this function, and then this is an 8-layer, right, tuning the thickness simultaneously. They ask us to make this device, right, and you will achieve whatever the requirement you want. And then this is the simulation curve, right? You can see there is a red, green, and also red, blue curve. So this is a white light here, okay? And this is our experimental results, right? Very close to the simulation. You have no other way to create such type of tailored transmittance. And this is why now we can get even higher performance device with very good color rendering index. Recently, we also introduced this angle-dependent capability, right, to our modeling. This is more close to the real application because our sun come out, right, and then kind of fall. They have a different spectrum and different angle. And the important thing is, right, the power, the solar panel installed in what type of angle and how much power you can generate over the day is what considered in the real case. So we also have this capability. So anyway, this high throughput optical modeling can potentially apply to many different areas. We are working with one of the largest glass company. They are working on this low E glass, right, low energy glass. They also have many layers, right? They want to tune the color, right, but also try to isolate the heat, right? So we are working with them to improve their device structure, right? You can also, this is kind of another company working on this face ID recognition. They want to have a highly sensitive, right, photo detector at the 940, 950. So we can also design the architecture with this localized light on that. And there is other application. Wherever you have this microcavity application, we can always use this high throughput method to design whatever the spectrum you want, okay? And recently, we also have another breakthrough, right? We are also trying to extend this application for LED. So as I mentioned, I also work on perovskite LED. And in this case, we try to design a white LED with good efficiency. Now we can get up to 10%. The best white LED now is around 1%. So it's a 10-time improvement of that. Okay, so here is a kind of a very quick summary of this semi-transparent solar cell. Inorganic one doesn't really have the unique properties to use for the semi-transparent solar cell, and they have a relatively low performance and also transmittance. But for OPV, you already get performance maybe three times better than that. Okay, and of course you have many different possible applications. How much time do I have?
Maybe 10 minutes.
10 minutes. Okay.
Including the FAQ.
All right, I will speed up. I only have maybe small session left. Okay. So this is one thing I would like to highlight. We can also introduce heat insulation properties, right? Now a lot of low E gas, they are trying to have this reduce the heat into the house. We can also combine this property with the power generation one. Okay, so that's why in China the most the Ministry of Science and Technology actually opened a new program, right, for this particular application. So finally, I would like to talk about stability. Stability is extremely important, particularly now we have a high performance materials. So my group also designed this solar simulator, combining this LED light with white light and also infrared light, so that we can match with the absorption spectrum or closer to the solar spectrum to do this long time, right, stability study. And we test a lot of new material, non-fluorine acceptor. Some of them degrade very fast, but some of the material actually is quite stable. Therefore, we try to understand why, okay? And the first one, we are selecting a series of material. This is the donor material. This is 3 different types of acceptor material. To do this study, we use an encapsulated device isolating this water-oxygen effect. So we are trying to understand the miscibility effect of these 2 type of material on the morphological stability under illumination. So we can find that for the materials, one of the material actually drop very fast, right? The other material is more stable, and we can use this so-called the Florey-Huggins parameter to give you some idea about the miscibility of the material. And this kind value, when 2 material is more miscible, the kind value is smaller. So that means, right, if they are more miscible, their morphology are more stable, right? And then now, right, you can have this maintain a pretty good stability. And then if the material is kind to phase segregate, right? Then when you have light, we provide energy to that, they start to degrade, right? The morphology for this age divide degrade significantly. So that's lose the interface, and then the performance continues to drop. So the interface between donor and acceptor material is one important factor to govern the morphological stability of the device. The other interface I'm looking at is the electro and the bulk heterojunction interface. We are using zinc oxide as the bottom electrode, and you know that in organic material, a lot of time is quite incompatible. Therefore, we introduce this fluorine self-assembled monolayer, trying to covalently bond, right, an organic electroactive molecule to the zinc oxide surface, right? I think Johnny knows this very well. I think he has a long time Nature material paper talking about self-assembled monolayer modification of the inorganic material. So what we find out that is when we have introduced this fluorine cell compared to the one with the pure zinc oxide, the stability further improved. It's highly stable, okay? And of course, right, when we're trying to extend the stability, we use this T80 lifetime, which means from the original efficiency go down to the 80% of the efficiency, how long it takes. And this cell modified device has the lifetime, right, up to 34,000 hours, which means if we consider every year we only have 1,500 hours of lifetime, this can be 20 years of lifetime. And of course, this is not new, but this is new to evaluate the stability, right? We use this strategy to improve performance 10 years ago when I was still in Alex's group, okay? And of course, right, we are trying to understand why. We see that with this cell modification, the fill factor continues to increase during this illumination, and then eventually they plateau. Current density is decreasing a little bit, so eventually they form a FET. They balance the effect for the power conversion efficiency. but for the unmodified one, right, both field vector and JSE is decreasing. And of course, we know that it probably is due to the morphological effect. So therefore, we also use this GREX trying to evaluate after this photo aging for the pure single site device. You can see the pi stacking of this non-fluorine acceptor is decreasing after photo aging, and then the amorphous region of the polymer also increasing. That means the morphology is degrading. Okay. However, in the case of this SAM-modified device, we do not see any degradation of this non-fluorine acceptor, but they have further improved of the stacking. Okay, that means that fluorine at the interface is promoting crystallization of the acceptor molecule when compared to the single site. That's why right now we can have improved packing of the molecule, we improve the mobility, it improves the field vector. That explains why we increase the field vector. But when we crystallize, we reduce a little bit of the interface, right? That's why we get the current decrease until they kind of plateau out. Okay, so this is another strategy that we can use to increase the OPV lifetime. Okay, and this is now is the longest lifetime with decent performance. So the last two slides is talking about this module design, and we are also working on the translation from the laboratory. We always doing this spin coating, but this cannot be applied for large scale fabrication. So therefore, we also work on this blade coating, optimizing the film formation properties, and also roll-to-roll printing. And you can see now we can make a larger module. This is one demonstration. When you put this module under the sun, you can charge up the iPhone. So eventually, right, this area is close to the surface area of the iPhone, and this can be also a flexible film, so you can even integrate into the cover of your cell phone. Okay, this is another example for the semi-transparent, right, OPV module. Okay, as I mentioned, I also have collaborator, right, in Germany who is really good on the module development. So we actually work with them, providing some of our protocol for high performance device. They are corresponding to make this large area module. And you can see for OPV only 2 records, right, in this module efficiency aerial chart, right? One is a Toshiba company in Japan a long time ago, but now we get a new data point, right? This CAE Bayern, right, in Germany, working at around 12%. So this is so far the champion module, right? They make in CAE Bayern. And as I mentioned, I am also initiate this innovation center on roll-to-roll printing. So I have worked with our partner for 2 years to design the right machine, and it's kind of delivering right now. So this will be a complete roll-to-roll printing machine with this laser patterning capability and lamination capability. So that's why I think it will be very excited if we can introduce high performance material into module demonstration. With that, I would like to summarize my talk. I think I can convince you, right? OPV still have a good future, right? Particularly for their efficiency. They are skyrocketing in the past 1 to 2 years. Now the performance 17 to 18%, but with the new understanding on the molecular design, I think we may be able to improve it to the 20% region, which make it very competitive, right? And also for the stability, we find that in some cases it can have a very good stability, but now the challenge is we still don't fully understand all the degradation mechanism. Particularly, we need to introduce this strategy into the state-of-the-art material so we can get high performance, high stability together. Okay, and new application, we know we have identified the right application, and then I would say commercialization is possibly within the next couple of years. All right, so this is all of my talk. Thank you.
Okay, so thanks for the wonderful talk by Professor Angus YIP.
Sorry, most of
That's
the time.
okay. Yeah, it's so interesting about fundamentals all the way to niche applications. So now open the floor to questions.
Can we ask questions?
Yes, sure.
Yes.
First of all, I'd like to say I like your Hong Kong English because we have the same accent, right? So, I have a question from you. So, semi-transparent solar cell. Yes. The concept of solar cell and transparent are really opposite concept. Because transparent, you want all the photon transparent, passing through your materials. And however, for the solar cell, you have to absorb as many as the photon you want. So that's why the existing solar cell, they're all not transparent. Right? Yes. You don't want to waste the photons. Now, so in case you can have a transparent solar cell, only two ways. One is your absorption band is in infrared, okay, infrared region or in UV, all right. But you got a problem if you got your band structure in the infrared, because you generate heat on your materials. Sunshine is shining on your material. The highest temperature is like 100 degrees C. Then you have to worry about the stabilities of your device. That's one concern. Now, if you move your band to UV, okay, there is not too much UV in the sun, right? So the transparency, I'm not sure. I'm not sure, and especially you show your example of transparency. It looks like in the top comics, it's blue color. It's not solar cell. It cannot be solar cell.
Maybe I can explain a little bit. Okay, so I think it's a balance, right? Of course, if you want to harvest as much as light possible, you want to make an opaque device, black device. Okay, so their performance can be higher. But we can also, particularly for the organic material, as I kind of mentioned, they can really have a localized absorption in the infrared, near infrared, not all the infrared. Okay, you will still want them to have a decent bandgap so that they can generate decent VOC. But that one, we can really leave the visible region to be transparent. So that is the unique properties. I think you can have good light harvesting, but without sacrificing too much of the photocurrent. And that's why we also trying to develop the optical engineering approach. We can easily tune whatever the color you want with the maximized, right, photocurrent and also transparency you want. Okay?
Yeah, but one of the problem, if you have your bandgap in near IR or IR, another problem is very fragile to UV. Usually, it's very weak to UV.
Yeah.
So
but for most of the solar cell, you need to have a UV filter. UV-Q, right? Even for inorganic material. Yeah. So,
yes.
So you must have the UV filter.
Okay.
So any further questions or any questions online? Do we get
No. I mean, I have some questions. Is somebody else? Okay.
No.
So it sounds like for a lot of your applications, you talked about you doing these thin film technologies, and you talked about how you want a good crystal structure, right? You want the right alignment. So by playing with the deposition conditions, you can change the crystallographic texture of these materials. And so is that a variable you actually use in the deposition process?
That is a huge area, how to control the morphology in the right nanoscale phase separation. You can have a lot of strategy to do that. Someone can use a thermal annealing, use different solvent, or even additive, right? You can control the crystallization of the individual phase, right, to achieve the final optimized morphology. But as I also showed that, your optimized morphology for performance may not be the optimized morphology for stability. So this is striking at the balance, right? How you can simultaneously to achieve both of them. And of course, we can have other strategy. For example, introducing cross-linking. You can first, right, make the good morphology, and then you can cross-link them, right? Hopefully without destroying its electrical properties. So now you can fix their ideal morphology.
But you were showing examples where you said some case, for example, spin coating, other case you had like a doctoring blade goes through. So putting it like using like a doctoring blade, there you're applying shear. When you apply shear, you can, I would imagine if you saw a crystal like this, you turn it like that by the viscosity of the material. Do people optimize this in the deposition?
There are a particular field working on this different way of coating, right? They can introduce different technology for the coating. I would say in the case of OPV, I don't know whether the orientation, you really want them to have a preferred orientation in this shearing direction, because you want them to have a vertical orientation. The best case is a phase-on structure. Right? This phase-on, you have better light absorption properties and then charge transport properties. Yeah. Of course, ideally, if you can design an organic material, have a high dielectric constant, they can self-dissociate the exciton.
Right.
You don't need that bulk junction. It will just act like inorganic material. And we see that the new kind of design of the non-fluoring acceptor already getting closer to that stage.
I have two questions about the optimization. Talking about the modeling. Does anybody else have a question?
No, so far.
Okay, so in the optimization, a couple of things. Often when you're doing optimization, if you've got many variables, you have many minima in the function, in your objective function you're trying to minimize against. Right? And when you have many minima, there is usually an extremum that in principle you want to maximize efficiency or something like that. But very often there are many minima which are very similar. And so in designing devices, since there's some randomness associated with the processing, sometimes you don't want the extreme minimum, you want a robust minimum. Which is to say one which will be, if you don't get it exactly right, it still performs very well. So that may be a very broad minimum, as opposed to the global minimum may be very sharp. How do you look for these robust minima instead of extreme?
That is a good question, but I would say with the optical engineering, we may be a little bit different from the material modeling, okay? And even if you look at the data point again, right, 14 million data point, right?
Yeah.
Even at the optimum one, there are many data points very close to the optimum.
Right, but just because you have many points in the same place in that space doesn't mean it's in the same places in the processing space. For example, small variations in thickness of a layer, or variations on a wafer from end to end. You know, is it going to be robust with respect to things like that?
We didn't do that analysis, but from the data point, we can actually ask the computer to pick up. For example, if you have a 10 nanometer difference on the variation, we can select those data points and then plot it out and then evaluate that.
The last thing on the optimization is all these optical calculations you're doing are all one-dimensional stacks.
Yes.
But you have a large sheet. Is there any room? Are there any cases where doing patterning in the other orthogonal dimensions where that could be things? I think about things like these sort of stealth kinds of.
Unfortunately, our model only works for planar structure, so we just make an assumption they are very fat for each layer, Indeed, they are quite fast for this one. But if we want to modeling something with structure surveys, then we need to apply the the other type of modeling.
Yeah.
But we didn't
FTDF.
right?
FTDF.
We didn't combine these two methods. I think we have some difficulty for doing that. Yeah. If that can be combined, we can even expand it to structure surface.
Okay.
Okay, so any further questions? Okay, so if not, then we can thank the speaker, Professor Yip, again.